So I'll get started. Before I start, I'll just go through some of the housekeeping stuff. First, every presenter will get 12 minutes of time. I'll give I'll just make a beeping noise on my phone before 1 minute, so that you know that you're almost towards the end. After after 12 minutes of time, judges will get 5 minutes to ask questions, followed by 3 minutes of time when judges will be working on the scoring. And at that time, if there are any questions from the audience, I'll ask them. For the audience, I'll say you can post your questions in the chat. I'll get them from there. And for the judges, as soon as the presentation is over, you can just unmute yourself and ask questions. To make the distraction as least as possible, I'll keep my camera off. And if during the presentation, other participants could do that as well, I would really appreciate that. But the presenter and the judges can keep their camera on if they want. Finally, I will control the slides. So for the presenter, as soon as you need to go to the next slide, just give me a verbal cue and I'll change the slide. And that is pretty much it. Does anyone have any question?
Yes, I have a question. My
Yeah, sure.
slides have some transition, like
Yeah.
especially slide 5 and slide 8. So I would need you to click because like I cannot explain without that transition. So
Okay, so I'll for that um, if you can give me like say click or change the slide, I'll do it. Otherwise, if your camera is on and if you just nod, I'll uh, try to monitor that uh, and 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 change the animation.
sure, like it's a slide 8 that is like more important. So
Okay,
I
slide
would
8.
like to pitch in a little bit.
Yeah,
So
sure.
while you are queuing Ranit to change your slide, you can use words like next, advance, proceed. One word should be enough, and he should be able to do that. Even for animation, even if you just say next, advance, start, or something, he should be knowing that it's time to change. So I think that should help.
yeah, thank you.
All right, with that, we have our first presenter, Alexis Pascaris. Did I pronounce your name correct? I'm sorry if I'm not. And the floor is all yours.
Thanks, Ranit. Hello, everyone. Thank you all for making the time to join today. I will be presenting my thesis, which is titled The Social Dimensions of a Technological Innovation, Agrovoltaics in the US. Next slide. Here's a roadmap of where we're headed. I'll start by setting the big picture context of my research, and then I'll give you an introduction to agrovoltaic systems. I will present 3 empirical studies, and then we'll have time for questions at the end. Next slide. This graphic is from the Intergovernmental Panel on Climate Change report on carbon and other biogeochemical cycles. The report identifies the dominant man-made drivers of climate change are the use of fossil fuels as an energy source and land use change, particularly agriculture. Results from these expert reports suggest that the most direct pathway to climate change mitigation is to find sustainable alternatives to conventional energy and food production. Luckily, we have an emerging technology that precisely addresses this dilemma. Next slide. This emerging innovation is known as agrovoltaics. Next slide, please. And agrovoltaics combine agricultural production and solar photovoltaics, or solar PV, into a single land use system. This renewable technology deliberately maximizes the solar resources available on a plot of land, effectively increasing land use efficiency and generating a dual revenue stream. Next slide. Agrovoltaics can either consist of solar integration with native pollinator plants, crop production, or with grazing animals, such as sheep for vegetative maintenance. Next slide. Given agrovoltaic systems are a novel technology, there is currently a wide range of research investigating their technical and economic feasibility. Many experimental and commercial applications are demonstrating the viability and the crop-related advantages of the agrivoltaic concept. However, there is still work to be done. The broader realization of agrivoltaics will entail taking these experimental projects out of the laboratory and placing them in a social context. In other words, the advancement of this technology cannot be pursued absent of socio-political considerations. Next slide. So this is where my research comes in. I've been investigating agrivoltaics from a social science perspective to identify the socio-political opportunities and barriers to diffusion. So my research is based on a case study in which we are investigating the viability of a novel agrivoltaic concept, co-farming pasture-fed rabbits and solar PV. And this includes studying the technical, environmental, and social aspects of this application. But my thesis is focused on the social component of this project. I've been using qualitative interview methods, conducting policy analysis, and employing quantitative survey research to identify the socio-political opportunities and barriers to agrivoltaics. Let's look at what I've discovered. Next slide. This article is published in a special issue of Agronomy titled Photovoltaics and Electrification in Agriculture. The objective behind this study was to engage agricultural professionals using qualitative interviews to identify opportunities and barriers to farmer adoption of agrivoltaics. So I interviewed a total of 11 agriculturalists and asked them about their perspectives on this technology. Next slide. The interview data were analyzed using grounded theory methodology, which is standard among qualitative researchers. The identified barriers and opportunities are as follows. Above all, the fundamental challenges are related to long-term land productivity and impacts from solar infrastructure. Participants also voiced the need for systems to be compatible with their farming practice, but flexible enough to accommodate future needs. Majority of the identified barriers centered on the challenge of navigating around permanent structures while keeping the land productive. Next, please. Just click for the animation. Thank you. But many of the barriers related to land productivity and impacts from infrastructure show opportunity for further hardware innovation. There are innovations that include solar racking systems that can be manually adjusted and semi-transparent modules that allow more sunlight to penetrate the soil. Such innovations can minimize impacts on farming productivity and demonstrate the importance of integrating farmer concerns in system design. Solar developers seeking to increase farmer adoption of agrivoltaics can consider these findings and tailor their technology to meet the needs of farmers. Next slide. We'll change perspective now and we'll investigate what solar industry professionals think about agrivoltaics. This study is titled Integrating Solar Energy with Agriculture, Industry Perspectives on the Market, Community, and Socio-Political Dimensions of Agrivoltaics. It's published in the Journal of Energy Research and Social Science. The intent of this study was to draw insight from solar industry professionals about the opportunities and barriers they perceive to be associated with developing agrivoltaic systems. I use the same interview data collection and analysis methods as the previous study. Next slide. So analysis of these interview data found that the barriers to development revolve around complexity, meaning that these systems demand added layers and time in design. In addition to this complexity, participants also raised concern around risk, safety, liability, and the hazards associated with hosting a farmer on an electrical site. Participants also warned me about community resistance to solar projects on agricultural land and localized zoning restrictions that would disallow this type of development. Click, please. But many opportunities were also identified. My participants explained to me that because these projects retain agricultural interest, they could increase support for development. This means that agrivoltaics present a really unique opportunity to increase the rate of solar development without threatening agricultural land. The findings of this study suggest that agrivoltaics can preserve farmland, increase the amount of solar being deployed, and uphold community well-being in the process. It's a win-win-win. Okay, next slide, please. Now let's shift gears one more time and think about opportunities and barriers related to policy. The last chapter of my thesis is an article titled Examining Existing Policy to Inform a Comprehensive Legal Framework for Agrivoltaics in the US. I am the sole author of this paper, and I've recently submitted it for review in a journal named Energy Policy. So let's consider that we are talking about energy systems on farmland. Therefore, there are implications on development at all three levels of government and across energy and agriculture sectors. Agrovoltaics presents a multi-level and multi-sector policy integration challenge. And prior research in this field suggests that policy integration gets complicated because different regulatory regimes overlap. So considering this challenge, in this paper, I'm advocating that a comprehensive legal framework that aligns laws on solar energy, land use, and agriculture will be instrumental to the diffusion of this technology. Next slide. So the goal of this analysis is to outline an enabling legal framework for agrovoltaics by studying an existing state-level agrovoltaic policy within the broader US context. So using legal framework analysis methodology, I use the state of Massachusetts as a case study to identify if there are contradictions or restrictions at various levels of government related to solar development on farmland. Next slide. Based on the results of my analysis, here I'm outlining an ideal legal framework for agrovoltaics. At the federal level, there are no significant barriers to agrovoltaics, but actually opportunities. There is financial support for solar development from the IRS in the form of an investment tax credit and from the US Department of Agriculture as a loan or grant to farmers. Neither of these support mechanisms restrict development on agricultural land. So I suggest that agrovoltaics be jointly owned by both solar developers and the farmers so that both subsidies can be obtained to reduce economic barriers. Next slide. Next, I've based my recommendations for the state level off of the Massachusetts policy because they are the only state in the US with an incentive program designed explicitly for these systems. So they represent a logical case study. So first, a state level framework should include a renewable portfolio standard that includes a solar carve-out provision that would stimulate solar development. In addition, states pursuing agrivoltaics should consider designing zoning enabling laws related to commercial agricultural land and solar energy. By exempting these land uses from unreasonable county or municipal zoning regulation, states can effectively make it easier for agrivoltaics to be developed. But in my opinion, the most effective policy tool at the state level is a feed-in tariff. Any state deciding to use a feed-in tariff for agrivoltaics needs to make sure that the tariff rate is high enough to recover capital cost and generate profit. Or, as suggested by my interview findings, solar developers will have little incentive to pursue a project that is more complex without compensation. Next slide. When it comes to local governance, there are some strategies available to municipalities pursuing increased agrivoltaic development. And these include the establishment of overlay districts, agrivoltaic land use provisions, context-specific site requirements, and adoption of smart growth principles. Being proactive in planning for and allowing solar on farmland will be key to support this technology at the local level. Next slide. So overall, the findings of this analysis suggest that federal and state financial mechanisms coupled with favorable local zoning are the key features of an enabling legal framework. The results further suggest that it is legally feasible to align policy measures across energy and agriculture sectors for the purpose of supporting agrivoltaic development. What matters most is the local socio-political context and how subnational governments decide to regulate solar development on farmland. Next slide. Okay, so let's take a step back and consider the bigger picture here. By revealing the perspective of different stakeholders and outlining policy tools, this thesis sets a foundation to enable agrivoltaic development. To answer my original research question, I would say the key socio-political opportunities for agrivoltaics include the deliberate retention of agricultural land and rural interests, and increased local level acceptance of solar development. The key barriers are related to ensuring long-term land productivity is not compromised and subnational governance and regulations around solar development on farmland. This thesis supports the argument that in instances where it is appropriate to do so, leveraging a single plot of land for both solar energy and agriculture should become the conventional practice. If we want to mitigate the climate impacts of energy and food production, we need to implement synergistic and sustainable land uses. I have many ideas for future research in this field, but for the sake of time, I'm going to conclude. Next slide. Here I'm providing reference to the literature that has most significantly supported my work. And I'm also referencing the papers presented in this thesis, as well as those related to the broader case study project. You're welcome to ask me about any of these studies. Next slide. Of course, I must conclude by sincerely thanking my advisor, my committee, our project partners, and the US Department of Energy for making this research possible. Thank you all.
Awesome. Thank you so much, Alexis. Now I'll go to the judges for questions.
Okay, hello again. This is Mary. First of all, thank you very much for your interesting and informative presentation. And thanks for sharing the key points of your thesis with us today. So I heard that you said you used some interviews in your publications. How did you conduct your surveys?
Yeah, absolutely. Thank you for asking. I did skip over the details of the methodology just for the sake of time, but the interviews happened so when you conduct interview surveys, it's important to be aware of how you're contacting participants and so that your sample isn't biased. So I use a snowball sampling method, as well as theoretical sampling. So snowball sampling is a sort of like chain of referrals. You start with one person in your research network, and at the conclusion of the interview, you ask them for suggestions of other people that might be able to help. And in terms of theoretical sampling, that's when you purposefully sample a certain type of person with a certain characteristic. So that means, relevant to my study, I wanted to talk to people who have experience in developing solar systems or experience farming. So it wouldn't do me any good to talk to a governor, but I had to theoretically decide who would be relevant to my study so that the answers I found were relevant. Does that help?
Yes, thanks a lot. Thank you. Very nice presentation. Thanks again.
Thank you.
Yes, if I may, I will jump in with a couple of questions if you're done, Mary. You're done. So, Alexis, very good presentation. You were very well prepared and the presentation is well portrayed. But you emphasized a couple of barriers that preventing the implementation of this technology. What do you think will be the solutions for such an approach?
Absolutely. Well, I think it comes down to the user of the technology, and the user of the technology is going to be agriculturalists. So I think tailoring the technology or modifying or accommodating the technology to assist the needs of farmers will be really important. If we present them an opaque solar panel that doesn't allow solar radiance to penetrate the soil, they might not even want to have the technology on their property. So I think innovations in module technology and racking systems will be critical because they will ensure that the productivity of the land is not compromised. And that's kind of a big reason we're doing this, is so that we can do both energy and agriculture at the same time. So we can't compromise one over the other. So I think barriers is going to be related to like maximizing the efficiency of both food and energy on the same plot of land through innovations in module technology.
And a follow-up solution. So you were talking about solar cells. You look into implementation of batteries as well?
I'm sorry, could you repeat that?
You looked into the implementation of solar cells in agricultural fields. Did you know the batteries that are required to go with those solar cells and how farmers will look at those?
That's an interesting question. No, my research hasn't looked at battery integration. I think at a high level, I was assuming that these would be grid integrated systems so that the battery backup wouldn't be absolutely necessary. But I think in off-grid situations, including battery storage will be critical. And in terms of battery research, we're moving in that direction. So it will be much more feasible. But I personally did not consider battery integration.
I have no more questions. Thank you very much.
Thank you.
If judges do not have any more questions, I welcome the audience to ask their questions. Feel free to post your question in the chat. I'll read them, or if you want to unmute yourself and ask, that works. I'll wait for another 20 seconds. If you have any question, then please shoot them. All right, seeing no more questions. Thank you so much, Alexis, for your great presentation. I'll now move to the next presenter.
Thank you.
So
all.
next presenter is Sadaf Batul. She, and I hope I pronounced your name correctly. She is, her thesis is on closed loop predictive control of a multi-mode engine. And with that, I leave the floor to Sadaf. If you, Sadaf, when you're ready, just you can start presenting, and I'll start the timer as soon as you start talking.
Okay, I'm ready.
Awesome.
Good afternoon. First of all, I would explain, could you please click? First of all, I will provide a brief introduction and motivation behind this research in the experimental setup used in this work. Then I will explain the physics-based dynamic low-temperature combustion mode engine model development on cycle-to-cycle basis. Next, I will explain the linear parameter varying system and model predictive control development. And at the end, I will provide results and conclusion. Next slide. In spark ignition engine, spark plug is used to ignite the air-fuel mixture. Spark timing is used to control combustion phasing. Unlike spark ignition engine, low-temperature combustion modes use air-fuel mixture, which auto-ignites at the end of compression stroke. Low-temperature combustion modes offer better fuel economy, better thermal efficiency as compared to conventional diesel engine and spark ignition engine. Also, because of the low combustion temperatures, it prevents the formation of NOx and particulate matter. So in order to meet the emissions level and to improve the engine efficiency, the focus is on low temperature combustion modes. In homogeneous charge compression ignition engine, the air and fuel are mixed homogeneously. The fuel is injected during the intake stroke so that it has enough time to mix homogeneously with air. At the end of compression stroke, the air-fuel mixture auto-ignites at multiple ignition points. That is why the heat release rate is higher in homogeneous charge compression ignition. In partially premixed compression ignition, the fuel is directly injected during the early compression stroke, which helps in partially mixing with the air. And at the end of compression stroke, the air-fuel mixture auto-ignites. In RCCI engine, as the name suggests, reactivity controlled compression ignition, two fuels of different reactivity are injected via port fuel injectors and direct injectors. This reactivity gradient of fuels drives the combustion. Next slide, please. When compared with the baseline spark ignition engine, HCCI shows 9%, PPCI shows 5%, and RCCI shows 14% improvement in brake-specific fuel consumption. Also, these low-temperature combustion modes offer better fuel economy and emissions, but they have limited operating range. So this study provides a unified modeling and control platform for all the LTC modes. Next slide, please. The engine used in this study is a gasoline direct injection 4-stroke 4-cylinder engine with compression ratio of 9.2:1. All the experiments were conducted under fixed variable valve timing. Next. Intake air is heated using controllable air heater. The engine uses two fuels of different reactivity. All the three modes are achieved using N-heptane, which is a diesel surrogate, and isooctane, which is a gasoline surrogate. For RCCI mode, the start of injection of N-heptane is controlled. Rapid Pro and Micro Autobox are used to communicate with the ECU and the engine. Next slide, please. This is the actual experimental setup, which is used to collect the experimental data. Next slide, please. The parametric study has been conducted for all the low temperature combustion modes by varying the intake air temperatures, keeping manifold pressure constant, changing the premixed ratio, Premix ratio is defined as the ratio of the product of mass of fuel injected via port fuel injector and its corresponding lower heating value to the sum of the product of mass of fuel injected via port fuel injector and direct injector and their corresponding lower heating values. Start of injection for HCCI and PPCI were kept constant. However, for RCCI, it was varied. Fuel equivalence ratio is also varied. All the LTC modes are achieved with under lean conditions, as you can see. Next slide. First of all, based on the requested indicated mean effective pressure and engine RPM, the mode selector selects the mode specific to the least brake specific fuel consumption. Can you please click? The engine cycle, the engine is modeled by modeling all the engine cycle events, starting from the intake valve closing. The thermodynamic states are estimated by estimating the residual gas friction and residual gas temperatures, and the pressure and temperature at intake valve closing are estimated. The start of combustion is predicted by parametrizing the modified Knock integral model. This integral becomes equal to 1 at start of combustion. That angle corresponds to start of combustion angle. For RCCI mode, this integral is divided into two parts to incorporate the port fuel injection and direct injection as well. Please next. VB function is parameterized to predict combustion phasing for each LTC mode. Next. Polytropic relationships are used to estimate the thermodynamic states for at the end of exhaust valve opening and exhaust valve closing. Next. At the end, indicated mean effective pressure is computed. Next slide. So this is the schematic for the controller and the engine. So the engine outputs are combustion phasing and indicated mean effective pressure, which are being controlled. Based on the reference combustion phasing, indicated mean effective pressure, engine RPM, and manifold temperature, the mode selector activates the corresponding controller. Based on that controller, either premixed ratio or start of injection is used to control combustion phasing, and fuel quantity is used to control indicated mean effective pressure. The engine model is highly nonlinear in nature, so in order to implement it in real time, the engine model is linearized at one operating condition. But this system uses dual fuels of different reactivity, which that is why the model is linearized at different operating conditions as a function of premixed ratio. That linear parameter varying system is fed back to the controller, and in order to estimate the states which cannot be measured, such as temperature at start of combustion, the Kalman filter is used to estimate those unmeasured states. Next slide. To integrate linear parameter varying system, adaptive model predictive controllers are developed. The cost function includes the reference tracking and the cost on the control inputs. R are the reference signals, which are combustion phasing and indicated mean effective pressure. Y are the outputs of the system. Q and R are the tuning weights, and U are the control signals. Constraints on actuators and outputs are also applied. Prediction horizon and control horizon are kept at 5 and 3 engine cycles respectively. Next slide. Here are the results. As I told, combustion phasing and indicated mean effective pressure are the parameters which have to be controlled. Premixed ratio is used to control combustion phasing, and fuel quantity is used to control indicated mean effective pressure. Both step changes in both the parameters are provided, and controller was capable of tracking both the parameters with an average error of 0.5 crank angle decrease in combustion phasing and 7.5 kilopascal average error in indicated mean effective pressure. The controller performance for disturbance rejection is also checked by providing a step change in manifold temperature. The controller was capable of tracking combustion phasing and indicated mean effective pressure in the presence of disturbance. Next slide. Similar to HCCI, premixed ratio is used to control combustion phasing. So step changes in combustion phasing and indicated mean effective pressure were provided, and the controller was capable of controlling combustion phasing with an average error of 0.3 crank angle degrees and an average error of 5 kilopascal in indicated mean effective pressure. Also here, step changes in manifold temperature was also provided to see the disturbance rejection performance of the controller. Controller was capable of tracking combustion phasing and indicated mean effective pressure. Next slide. For RCCI mode, start of injection was used to control combustion phasing, and fuel quantity is used to control indicated mean effective pressure. For the first case, the premixed ratio was kept at 20. It was constant, and the controller was capable of tracking both the parameters. For the second case, premix ratio was modeled as a measure disturbance. Also, the controller performance for a range of premix ratio was tested by varying the premix ratio from 5 to 45. And controller was capable of tracking combustion phasing and indicated mean effective pressure. Next slide. Here I will summarize the work I have conducted. First of all, physics-based nonlinear control-oriented models were developed. Linear parameter varying systems were developed as a function of premixed ratio to encounter the nonlinear behavior of the engine model. Control-oriented models were validated under steady state and transient conditions. The average error in combustion phasing prediction is less than 2 crank angle degrees for all the LTC modes, and the average error in indicated mean effective pressure is less than 37 kilopascal for each LTC mode. Next slide. The controller reference tracking performance showed 0.5 crank angle degrees average error for HCCI mode in combustion phasing and 7.6 kilopascal in indicated mean effective pressure. In order to reach the targeted value, combustion phasing takes 0.6 seconds, which are 4 engine cycles to reach the targeted value, and indicated mean effective pressure takes 0.15 seconds, which is 1 engine cycle to reach the targeted value. For PPCI mode, both the parameters achieve their targeted value in 0.6 seconds, which are 4 engine cycles. For RCCI mode, combustion phasing takes 2 engine cycles, which is 0.2 seconds, and for indicated mean effective pressure, it takes 1 engine cycle to reach the targeted value. Next slide. Thank you. If you have any questions, they're welcome.
Okay, this is Eri. Thanks, Ada, for your nice presentation. Why did you specifically use predictive controller in your model?
So for all other controllers, we cannot incorporate the constraints. So here we have applied constraints on outputs as well as the physical limits of the actuators. So model predictive control is an optimal control technique which encounters the constraints.
Okay, great. Thank you. And I have one more question. So you talked about benefits of low temperature combustion mode, something like reduction in NOx emissions, but is there any challenges when you run an engine in low temperature?
So basically, the fuel and air mixture auto ignites, and because of the dual difference in the reactivity of two fuels, the pressure rise rate is much higher in low temperature combustion modes, and also in, the cyclic variability is more in low temperature combustion mode. So these are the challenges. That is why we are controlling combustion phasing and indicated mean effective pressure to provide a safe and a safe engine operation, as well as to ensure that the cyclic variability like, stays at the minimum.
Okay, thank you. Very interesting presentation. Thank you.
Thank you.
Thank you very much for that very good presentation. I have a couple of questions. So let's start with if you can summarize the overall conclusion of your work, what would it be?
So actually, as a first step, we have implemented we have provided a unified modeling platform for the control of HCCI, PPCI, and RCCI. As I mentioned, like there, when we did the parametric study, we figured out that there were some cycles which showed misfire and partial burn. So in order to take the advantage out, like to keep the emissions lower, if there is misfire or partial burn, we can get hydrocarbons out of the engine. So then there is no benefit of the emissions. So we developed the controller such that the combustion phasing is controlled, which provides us maximum indicated mean effective pressure as output, and also to ensure that the combustion is stable. And the second thing is we tried to combine these together into a single engine because these different modes use different type of actuators in different type of processes. As I mentioned, homogeneous charge compression ignition, fuel is injected in the intake stroke. For PPCI, it is during the compression stroke. For RCCI, it's during the intake stroke, and N-heptane is injected directly during the compression stroke. So we need different type of controllers. So I try to implement all the three modes into the same control platform.
Okay, that makes sense. Last thing is that, is there any improvement in the overall efficiency of the engine between the three models?
Yes, we like the next step is to implement these controllers on the engine. So this up till now, this is just a simulation study. So which is completed. The next step is to implement this on the engine. So I cannot surely say that, but based on the parametric study which we have conducted, on which we have developed these models and controllers, that showed 9% improvement in HCCI, 5% in PPCI, and 14% in RCCI as compared to baseline spark ignition engine.
I see. Okay, thank you. I have no more questions.
Thank you. Thank you.
Thank you, Sadaf. Audience, if you have any question, please post them in the chat, or you can unmute yourself and ask.
Hi, Sadaf, it's Udit. I have a question. Very nice presentation, firstly. So in one of the discussion, you said that the response is non-linearized and you have to linearize them, right? So what do you do to linearize them? Like, do you use finite difference, you use Fourier transform, or any Euler method or something like that?
No, I just computed Jacobian, and then I the basic linearization technique which we use is we differentiated with respect to the states and the control inputs, and then provided the differential equal to 1, we computed at the particular operating condition, and then we get the state space matrices out of it.
Okay, so I'm assuming, like, since you are making it from non-linearized to linearized, is there any difference in the curvature, or you are making it, let's say, such a small step that it does not make difference?
So basically, like normally what people do is they just linearize at one operating condition. So that operating condition only holds true for us for a certain range very close to that equilibrium point. So what I implemented is linear parameter weighting system. So I developed different linearized models which are function of premixed ratio. That covers the whole operating range. So that is why I was able to control the combustion phasing specifically for all the range of premixed ratio.
Okay, thank you. Yeah, that answers my question. Thank you.
All right. Thank you, Sadaf. Judges, are you done with the scoring?
Yes.
Great.
So should we score right at this time?
For this, for
I mean,
Sadaf,
should we
yes.
fill out the form or take a note as this time?
Yeah, like, are you done with taking
Yes,
notes?
I'm done. Yes, I'm.
Okay,
Yeah.
yeah, great. Thank you. All right, then thank you, Sadaf, for a great presentation. Now, the next presenter is Udit. Udit Sharma is from Mechanical Engineering and Engineering Mechanics Department, and his topic of presentation today is non-equilibrium thermodynamics approach to supercooling in phase change materials. Udit, the floor is all yours.
Thank you, Ranit. First of all, I would like to thank everyone who has joined for this presentation. And thank you, GRC, for organizing it. I know it's a tough time. So thank you for organizing this. And I'm really excited to present this. So, Ranit, I think I'm good. I can start. Okay.
Yeah.
Yeah. So as you can see, the topic of my presentation is non-equilibrium thermodynamics approach to supercooling in phase change materials. So the topic itself says that I am not going to implement, I am already going to negate the use of equilibrium from the aspect that I am implementing it. Next. So the purpose of this presentation is not to use a lot of technical jargon. I want to have the audience know something new. I want them to learn something new so that at the end of the day, you will come here and grab something that you have not known, though I will go into the detail at the later stages of this presentation. So these are the outlines. I will be discussing about the introduction and application. Thereafter, I will be discussing about the problems and the types, enhancement techniques, the supercooling, and the objectives of the work. Next. So the very first question arises, what is PCM? PCM are phase change materials, and these are the type of thermal energy storage that are passive in nature. When we are using the word passive, it means that you do not need any type of moving part in it. Okay, there is another type of thermal energy storage. Those are known as sensible energy storage, in which you have to provide the temperature difference across it. These do not require any temperature difference because you are going to store the energy in the form of the latent heat, which is during the phase transitions. Now the question arises, why do we want to use PCM? Next. There are three reasons for it: the temperature range, volumetric change, and the energy density. These are the primal considerations when you are looking for a thermal energy storage. Temperature range, that is wide. Like you can work at the cryogenic scale to a very high temperature range. Volumetric change is very low since we are only looking into the form of only the phase transitions. So there is not much volumetric change. And energy density. It is a well-known fact that the latent heat of any substance or any material is way higher than its sensible heating. So the energy density is in itself going to be high. And since we have already discussed the volumetric change is low, the energy density is directly related to that and it will be high. Next. So the applications are majorly presently that are being implemented are in the form of out of phase electricity demand. So when the demand is more and the production is not there for the electricity, in that case, you can use the phase change material energy storage for as the backup. The other usage are like in the solar energy storage, electronic cooling, and the space air conditioning. Next. So this picture is meant to show you that the scale of this phase change material application is not only limited to the micro scale, it is also applicable to the large scale. So in the top two pictures, one on the left, you can see that there is a heat sink. It is used in the pulse, single pulse signals in which there is a lot of heat generation in a single amount of time. The one to the right talks about the electronic cooling. So this is also a heat sink. The one at the bottoms, and like these are two at the bottoms, one is used in solar power plant and other is used in the solar water heater. So you can see that there is a wide range of applications that we can have. Next. So phase change material types. So there are basically three types of phase change materials. One is organic, other is inorganic, and the third is eutectic. So organic phase change materials are the ones that directly are in the form of fatty acids and paraffin wax and vegetable oil. The ones that you make by a combination of different ingredients, that is not considered organic. Those will be inorganic. So for example, metallic and salt hydrates using potassium nitrate, the combination of potassium nitrate and sodium nitrate can be used as the inorganic. And the third is eutectic. You can use a combination of these two, like organic, and inorganic, or two inorganic. All these three combined combinations can result in an eutectic. In that case, you can take the advantage of both the properties of the phase change materials. Next. So since you have a technology, any material, there are problems associated with it. And the major two problems that it has is the low thermal conductivity and the supercooling. Next. Yes, so supercooling. So this is the major work of my discussion, and I will discuss about it in a bit. But before that, let's talk about the low thermal conductivity. Next. So the problem with this phase change material is that they are not very quick in responding. So what happens that when you are trying to heat it or cool the phase change materials, they do not react very quickly. It takes time for them to melt, and it takes time for them to freeze. So what happens that we are not able to get the quick response that we need. And you can see that the equation that is in front of you, this is known as the Fourier's law of conduction. And what we want is to increase this value of Q as much as possible. And you can see that there are three different parameters in this. K is the thermal conductivity, A is the area, and delta T is the temperature difference. So all the techniques that are implemented to improve this thermal conductivity are oriented towards these three. So the performance enhancement technique first is like increasing the heat transfer surface. So looking into this equation, you can see if we increase the surface area, then the heat transfer rate will increase. One thing. How can you do that? By using fins, by using any geometrical constraints, and by using any extended surfaces. The second is increasing the thermal conductivity. You can add different type of nano additives, different type of high conducting materials to make them to increase the thermal conductivity. And you can actually use a metallic mesh to increase that. The third is improving process uniformity. So this term process uniformity is with respect to delta T, in which we want to make sure that the temperature is uniform throughout and there is not much different and the fluctuations are not there. You can implement it by using different combinations of phase change material by their changing melting and solidification temperatures. Next. So phase change material supercooling. Next. So what is supercooling? The very first question that arises is, so supercooling is a stage in which the material does not freeze when it is supposed to freeze. So let's consider as an example that you have water. The water at atmospheric conditions should freeze at 0 degrees Celsius. But let's put it in the freezer and you see that the temperature is -2, but still the water does not freeze. What is the reason for it? You do not know, but it does not freeze. So that is known as supercooling, means you are unable to solidify something when it should. So this term is known as supercooling. After effects of supercooling, now let's say that I already discussed that the phase change material is implemented in a lot of fields. Specifically, one of them is space air conditioning. So when you are using in space air conditioning, you want the temperature of the room to be stable at a particular temperature. If supercooling happens, the cycle will change. You want to solidify at, let's say, 20 degrees Celsius. It won't solidify at that point. The room will get colder and colder, and it will be uncomfortable for the people inside. It is really bad and catastrophic if you are trying to utilize it, let's say, for an ICU. You cannot use it in ICU because it will be very sensitive to the bacteria and the viruses, and it will mess the things up. Next. People have came across to reduce supercooling, but let me tell you that no one has eliminated supercooling. They have tried to reduce it. How they have done it? By adding materials that can start the nucleation so that it crystallizes faster. Other methods are like you can provide the wire disturbance, porous material, and varying surface tension. So these are the various ways that people are trying to reduce supercooling. And the third one is like external fields in which you implement magnetic field. If the phase change material is implemented by it, then the supercooling can take place. Next. Now the question is why supercooling occurs. And you can see specifically I have written that no one actually knows the answer to this question with evidence. Though there have been theories about it, that supercooling occurs due to the lack of nucleation sites and due to the rate of the cooling and all those. But actually, there is not a single fundamental theory that can justify with the evidence that supercooling occurs because of this. Next. However, I have my own hypothesis. What I personally feel that the supercooling occurs due to the non-equilibrium aspect that is associated with it. When we consider the phase change operation, we consider it to be isothermal. But theoretically, it is isothermal. But when you will go down, dig deep down, and you will look at from the non-equilibrium aspect, you will see that it is not isothermal. And if supercooling is actually related to the nucleation sites, then why would you see supercooling after a lot of thermal cycles? Why would you see supercooling when the size of the material changes, when the shape of the material changes, when the curvature changes, when there are changes in the gravity? So nucleation is not the only reason, right? Next. So here, what I am trying to do is relate two things, the entropy generation with the supercooling. So when you will look the interface of any material, either it is during evaporation, condensation, or during solidification and melting, you will see that at the interface, there is an inconsistency. There is a interfacial layer, and there is excess entropy generation at that point. What happens that when that flux is being transferred from one phase to the other, there is entropy generation, and that entropy generation is, in my opinion, the reason for the supercooling. Why I am saying that? Because supercooling is basically nothing but the loss of the work that has already been put in. I already told you in the previous discussion that you want the you want the material to freeze at 20, but it freezes at 16. So it means you have to extract more energy out of it by 4 degrees Celsius. What happens there? That energy is lost. It is not being used. Still the material will crystallize, but that sensible energy is lost. And I am relating that lost work corresponding to the entropy generation. Next. So now my purpose of this presentation was to show you what we are going to look into it, and this is what we have discussed. I am assuming you guys have learned something new, but now since this is a project and I would want to go a little bit more into the equation side, so you can go to the next slide. And these are the equations that I use, and these are the equations in which you are using the coupling coefficients, means the combination of the heat fluxes and the forces to get the relationship. And this is where the entropy generation comes into play, sigma s. Next. So the objective of my work is to investigate supercooling from the non-equilibrium approach, one thing, and the second is I want to provide more understanding for the anomalous behavior, like why does it depend on the temperature, on the thermal cycles, why it depends on gravity and other things, and the volume. Next. These are the references. Next. And next. Yes, thank you. If you have any questions, please.
Mary, I will start this one.
Okay.
How does this research improve on existing understanding of supercooling?
Can you pardon?
How does this research improves on existing fundamental work?
So what happens is, like, there are a lot of experiments that are done on, let's say, micro scale, that you are using DSC and other approaches to find how any material or a phase change material is reacting. But when you are using it at the macro scale, or you are using it, let's say, on a solar concentration plant, those do not match. The supercooling that you can avoid and can provide the results from the small experimental point of view do not match very well with the applications that are being done actually. So what we want to scale the micro things to the macro thing. And how can we do that? By having a consistent approach that can create a coupling between those. And this is what non-equilibrium thermodynamics do. It takes all the fluxes and forces that could be the reason for it, and they couple them all together, and you can come across a relationship that can scale the things that you are doing the experiment right now, and you can scale it to the higher scale.
Good. I have no more questions.
Okay.
Okay, so Stas already asked my question and you answered. Okay. Thank you. Thank you for a great job.
Yeah, thank you.
So I stole your question. I apologize for that. So
oh, no problem. Thank you for actually asking it.
I have another question there. Give me a second. Well, maybe there's a question from the audience. I will come back to that.
I have a question.
Yes.
Although that was a very nice presentation, I had just one question. Like, are you studying PCM in general, or are you specifically studying only one material or some materials? And I would like to know your application as well. Like, what is your target market technology?
Okay, so answering to your very first question, so this is a very generic work that I am doing. It is not restrained by any type of material. it is basically a work that is done on supercooling. Any material that undergoes supercooling under different circumstances, this work is applicable to all of those. And the second thing was, where is it applicable? So I will say this is not directly applicable to, let's say, electronic cooling or any power plant. But what it will help is making the applications more design oriented, optimizing them better. Because I told you that the things, the experiments that you do at micro scale do not match up very well at the grand scale that people are working on. And if we can eliminate that gap, then the design consideration can be better and you can provide better like applications of it. Make sense?
Yeah, thank you so much. And I have one more question.
Yes.
So, are you only using simulation techniques, or are you conducting some experiments as well to?
So as of yet, I have not done any experiment, though I have certain experiments in my mind. And this is the work that I have done in like last 2 years. And this is all literature review and all my hypothesis that I have. I am going to implement it as soon as I will have more data to do the experiments and provide my hypothesis and provide a reasoning for it. So right now I am unable to get the correct form of the coefficients that I should use.
Okay.
Okay.
Yeah, it's very interesting topic though.
Oh, thank you.
Thank you for your presentation.
Yeah.
Okay. One simple question.
Yes, sir.
Does this work can be applied for energy storage as well?
Yes. So recently there was a meeting by NREL and the energy. I forgot the name of the EPS. So the biggest challenges in the field of thermal energy storage is actually supercooling. So even in the Lawrence National Laboratory, they are working towards this field dedicatedly to actually have a better understanding of why supercooling is happening at such a grand scale. And their target by 2030 is to see if we can eliminate it or not. And if we cannot eliminate it, there should be a way in the design to make sure that it does not happen at instant.
Good. No more
Okay.
questions.
Thank you so much, Udit. Thank you so much, judges, for your questions. Audience, do we have any more question for Udit?
Thank you, Ryan.
So I'll just wait 20 more seconds to see if we have any other questions, and I'll give time to the judges to do the scoring.
So I would like to one more time thank you three, Udit, Sadaf, and Alexis for your great job. And thanks audience for joining us today to actually participate in this speech. Thank you, everyone.
Thank you.
I will act, Mary.
Thank you so much, Stas and Mary. You just did the job for me because in the end I was going to thank everyone, the judges, the three presenters, and the audience for joining us. Um, to echo what Mary just said, thank you so much everyone for joining. Udit, Alexis, and Sadaf, great job presenting. And Stas and Mary, thank you so much for joining us today and judging our presentations. For the audience, thank you so much for joining. And there are other GRC events going on, other presentations are going on. Please feel free to join in those presentations and see the research that the graduate students are doing here. And we have our GRC banquet tomorrow from 5 to 7. So I would request you all to join there and support the work that GSG is doing. All right, thank you so much again. I hope you have a great rest of your day. Bye.
Thank you.
Thank you. Have a good day. Bye.
Bye.